Yeah, so I guess we'll start today's lecture. As usual, unmute yourself and ask questions if you have any, since this is an advanced course. This should be the norm. And also, if you have any difficulties hearing me or anything, please let me know. So, yeah, here's a quick outline of today's lecture. So, we'll begin by a quick revision of Krw conjectures. We saw the statement in detail last time, and so the main thing for today's lecture is going to be this connection to communication complexity. So if you remember, the Krw conjecture is a conjecture about circuits, but one of the reasons it's in an exciting research direction is that it has deep connections to communication complexity. So we're going to see a result by Kashmir and Victorian, which connected circuit depth, which is what the conjecture talks about, to communication complexity of a specific relation. So this is going to be the main thing for today's lecture. And then once we say this connection, we'll restate the conjecture in terms of communication complexity instead of circuit complexity. Then I want to briefly mention a simplification called universal relation, which is going to be the theme of next week's lecture. But it's not too important. We are going to just see a quick definition, and then I want to play the adversary with this conjecture. So if you are a skeptic and you don't believe in the conjecture, so you might be wondering what are the best known gaps in the conjecture, what are there any counterexamples. So we're going to see an interesting example, and we'll also see that it needs a proof, and it's kind of non-trivial. It requires a bit of circuit complexity, and if time permits, we'll see the proof. And I don't know if everyone has background in circuit complexity. In case there's something that I cover that you don't understand, we can discuss over like office hours or some separate lecture, and I can also like post some notes, like links to some references in circuit complexity where you can find this. Okay, so let's start. So just to quickly recall, sorry. So the Krw conjecture, if you remember, was about this. Said that so given two Boolean functions, so one is on m bits of input, right, and another is an n bits of input. So I'm not going to repeat, but always I'm going to assume that f and g are non-constant functions. And we saw in the last class that if either of them is a constant function, the conjecture is clearly not true. So I just state here explicitly, but not anymore. Non-constant. Okay. Uh, we define this block composition of f and g, denoted by f compose g, which, if you remember, was a function on mn bits of inputs and produce 0 1 value. And the way we would like to think about this function, the input to this function is in the form of a matrix. So if you remember from last class, what we are going to think of the input to this function as a m by n matrix. So they're going to be m rows and they're going to be n columns, 1 up to n. So the output of this function is going to be uh, described in two stages. In the first stage, we are going to apply g on each of the individual rows of this matrix. So by applying g, you get a 0 1 value. G is a Boolean function, right? So you get, like, so I'm going to represent this by a vector. So you get a 0 1 value of, and they're going to be m 0 1 values. So that's the first stage. And to get the final output of the function, this is an input to f. So you apply f on this vector, so you get a 0 1 value. So f compose g is this one, right? So so we saw yesterday that depth complexity of f compose g is at most depth complexity of f plus depth complexity of g, and the conjecture states that In fact, it should be, sorry, this should be f compose g should be approximately equal to depth of f plus depth of g. We saw that this approximate inequality can be approximate equality can be defined in very many ways, uh, so that we still get the huge implication that p is not equal to nc1 if this conjecture is true. So I'm going to leave it as an approximate equality for now. Yeah. So here, this is just a quick overview of what the conjecture was, and today we are going to like connect it to communication complexity. So this is a connection discovered by Kashmir and Wigderson again in the 90s. Um, by the way, like references to these papers, I try to include in the notes when I post them. Currently, I posted drafts of the first lecture. I do some editing later in the week. Okay, so if you remember Kashmir, the conjecture is with another co-author, Van Ras. So this link was discovered by Kashmir and Wigderson, and then Kashmir, Ras, and Wigderson used this link to prove some interesting circuit lower bounds, and then in that paper they also make the conjecture. So what is this connection? So this connection is to communication complexity. So I just briefly, so I don't know how many of you have background in communication complexity. As I said, for circuit complexity, if you are unfamiliar with something that I discuss in today's lecture, please mail me and we can set up something and discuss, and I can share some resources or have a meeting with you. So just to give you the minimal introduction to communication complexity so that you can understand rest of the stuff. So the model of communication complexity that we are going to consider is called the standard two-party model due to Andrew Yao. So there are two players, Alice and Bob. Okay, so they are, so in classical communication complexity they hold two inputs x and y. We can assume without losses generally they're like n bit strings or something, and they have a function in mind. So there's some function which is known a priori to both the players. So that, let's say this is on n bits to n bits to 1 bit. So it's a function of x and y, and the goal of these players is to communicate as few bits as possible to compute this function jointly. And what are the constraints? Alice cannot see Bob's input and Bob cannot see Alice's input. Okay, so they want to like goal jointly compute f of xy with minimal bits of communication. So I'm not going to define formally like what is communication complexity, but this is the intuitive picture. So just to give you an example, for example, let's consider this function called equality. So given two strings x and y, equality is just asking whether the bit string x is equal to the bit string y. So this is 1 if x equals to y bit by bit on all the n bits, and 0 otherwise. So one trivial protocol, so their goal is to compute equality of x and y, and uh, a method that they can predetermine before seeing the inputs to compute x and y. It's called a protocol, and a trivial so I'm not going to define what a protocol is, but I'm going to tell you with an example. So a protocol for computing equality is as follows. So Alice begins the communication. So Alice gets x, Bob gets y. So Alice first sends her entire input x to Bob. Then Bob, so in this model we're going to assume that Alice and Bob has unbounded computational power. So we are not going to be interested in how long does it take for them to compute something internally. So Alice sends x, and then Bob compares if x equals to y. If it indeed is equal to y, uh, in the yes case, Bob sends 1 back to Alice. in the no case, Bob replies with 0. So here is a protocol that computes equality. So at the end of the protocol, both Alice and Bob know whether x equal to y or not. And the measure associated with the complexity measure associated with such a protocol, it's the communication complexity of this protocol. So we'll denote it by, so a protocol is generally denoted by capital Pi, and the communication complexity I'll denote it with CC. So this is slightly abusing the notation. So there are various notions of communication complexity that you can consider. Like in algorithms, there is deterministic, like in algorithms, there are deterministic algorithms, randomized algorithms, etc. Right? So in communication complexity also, you can think about deterministic protocols and randomized protocols, etc., etc. So for because of but the connection between circuit complexity and communication complexity obtained by Kashmir and Wigderson talks only about deterministic communication complexity. So we can just focus on deterministic communication complexity. So yeah, so what I was telling is that, okay, so communication complexity of a protocol is basically the maximum number of bits they send on any possible inputs. So it's kind of a worst case measure. So it's maximum bits communicated over all possible inputs. So here, for example, in the case of equality, this protocol that I described to you is very simple. It, no matter what the input is, it just sends the same amount of bits between the players. So what's the complexity here? Alice sends x, which is an n-bit string. So that is, so this specific protocol, the communication complexity of this specific protocol is n bits for sending x and 1 bit for sending the answer. So this is n plus 1. And if you have seen communication complexity, you know that if you consider only like deterministic protocols for this specific function, there isn't anything better that you can do in the worst case. Okay, so in some cases, like the trivial protocol that you can think of is also the best protocol that computes a certain function. So just as an aside, I want to say that this is also a protocol for computing any function. So here it didn't matter we were computing equality or something else. So the same protocol works as long as Alice and Bob know x, the function they want to compute. Alice sends x, Bob computes f of x comma y because Bob has y and he has received x from Alice, and then he can compute it completely, and then he can just send the answer back to Alice based on whether f of x y is 1 or 0. But for describing the connection obtained by Kashmir and Wigderson, we need to generalize communication protocols to things other than functions. So what's the generalization of a Boolean function? It's a relation. So as again, like as ever, I'm not going to formally define what a relation is. I'll first show you an example, and then I'll define it more formally. So I'd start with this specific relation that they are concerned with. It's called the Kashmir-Wigderson relation. Okay. From now on, it will be abbreviated as KW. KW is Kashmir-Wigderson, and KRW is Kashmir as Wigderson. Sorry, Wigderson. So here is, so what is this relation? So here is the communication problem. So the players Alice and Bob are given some Boolean function f from, let's say, 0 1 to the n to 0 1. Okay, and what is the input to Alice? Alice is given an input x such that if you apply f on x, it would evaluate to 1. So this is an equivalent way of writing f of x is equal to 1. Okay, so Alice is given an input where this given function that is known to both the players evaluates to 1, and Bob is given an input y which evaluates to 0. So it's sort of a promise problem. So Alice only gets inputs, n bit strings of a certain kind, and Bob gets n bit strings of another kind, right? And they're disjoint, y equal to 1. So what is the goal here? So usually in the standard communication complexity setting, you're given two parts of an input to a Boolean function, and then you want to evaluate this Boolean function. Here you're given two different inputs to the same Boolean function. So the goal is not to evaluate this Boolean function. That doesn't make sense, right? Alice is given an input where the function evaluates to 1, and Bob is given an input where the function evaluates to 0. This is a mistake. It should be 0. So the goal here is for the players to find an index I, which is an index from 1 to n, such that xi is not equal to yi. Okay, so because f is an n bit function, x is an n bit string, and y is an n bit string. So the goal here is to not to evaluate some function, but they want to find an index where their inputs differ. Okay, so the first natural question to ask is like, why should there be even such an index? So the reason this problem is non-trivial is that because of the guarantees that they're given, because of the promise x is guaranteed to be different from y. So the reason is pretty simple, right? I mean, if x is equal to y, if x is not different, that means x is equal to y, then f of x cannot be different from f of y. So just it's a one line proof. Maybe I should not close this bracket. It's like, because if x equal to y, f of x cannot be, it cannot be the case that f of x is 0 and f of y is 1, because they're the same string. This is a contradiction. So hence, given this promise that Alice is given an input where f evaluates to 1 and Bob is given an input where f evaluates to 0, it's guaranteed that x and y are different. So if x and y are different as bit strings, there should be a single index where the corresponding Boolean values are different, right? So this is the Kashmir-Wigderson relation associated with a Boolean function. So we'll denote this by kw of f. Okay, so this is going to be a very important relation that we are going to analyze from this lecture onwards. So this would be a good point to pause and ask questions if you have any questions. Okay, if not, let me move on. So just one more thing, I'm going to informally define the communication complexity of Kashmir-Wigderson relation to be again, so among the protocols, so you can think of various schemes that would solve this problem. So these schemes are protocols. So among the protocols pi that solve kw of f, what is the minimum? It is the minimum communication complexity of any such pi. So if you remember, like when we defined the depth complexity of a function, we said that there can be more than one circuit that computes the same function, and the depth complexity is taken to be the best depth among all possible circuits that compute the function. Similarly, the communication complexity of a function or a relation is defined to be, look at all the protocols that correctly compute this function or relation and take the minimum communication complexity among all these protocols. Okay, so this is going to be the measure, and it's easy to see that this again, the protocol, the kind of protocol I described in the beginning works here as well. In general, like, so here is a protocol that can solve KW of f for any f. It just so here is a very naive protocol. You can do something better for most functions, and we are going to see what that is going to be. So given, so remember Alice is given x from f inverse of 1, and Bob is given x from, sorry, y from f inverse of 0. So Alice sends x, and then Bob can check, find find an index where x and y differ, and send it back to Alice. So this takes, so the communication complexity of this protocol, so this is one example of a naive protocol. So the communication complexity of pi is the number of bits that you need to communicate x, that is n, and I is an index from 1 to n, right? So to communicate an index, so to represent a value from 1 to n using binary bits, you just need log n bits. So this protocol has so the the cost of this protocol is n plus log n. This is completely ignoring what the function is. So if, so this is not the optimal protocol for a given function, but this sort of solves every Kashmir-Wigderson relation for every function. So we're going to see that if you, for a specific function, you can do something way better than this. Okay, and this is going to connect it to circuit depth complexity. So before we move on, are there any questions? Okay, if not, let me get to this connection. So this is a theorem by Kashmir and Wigderson. So intuitively it states that, so for any given Boolean function f, the communication complexity of this Kashmir-Wigderson relation associated with f, kW of f, is exactly equal to the depth complexity of f. Okay, so this says that if you want to understand the depth complexity of a Boolean function, it's enough to understand the communication complexity of this associated relation. So this is very interesting, right? I mean, we have connected, so this is like a bridge that takes you from circuit complexity into the world of realm of communication complexity. And in communication complexity we understand a lot more about computation than in circuit complexity. So this is one of the reasons this conjecture is very exciting, but it's also, so just getting a bit ahead of myself, that we're going to see later that the kind of communication complexity that Kashmir-Wigderson relation talks about is the communication complexity of a relation, and classical communication complexity studies functions. So there's a lot of differences also, so you need to develop tools that are custom made for relations, and that's the main challenge here. Okay, so uh, I'm not going to prove this theorem completely. I'll give you one direction of this theorem, and that's, and we'll see this with an example, and uh, maybe I'll give this as an exercise to do the other direction. It's not So once you see one direction, it will be clear how to do the other direction. And yeah, let's start off by seeing one direction of this theorem. So what do I mean by, yeah, so if it's not clear to you, the two directions I'm referring to is like the way this proof this theorem is proved. So first you prove that, so this like uh, so intermediate goals. So first you prove that communication complexity of the Kashmir-Wigderson relation is upper bounded by the depth complexity of f, and then you prove that the depth complexity of f is also upper bounded by the communication complexity of the Kashmir-Wigderson relation. So if you have these two inequalities, so the only possible relation between them is that they are in fact exactly equal. Okay. Okay, so what we're going to see in today's lecture is this part, and maybe this is going to be an exercise. Okay, so let's take a very concrete function and see this direction. So remember, our goal is to prove that the communication complexity of the Kashmir-Wigderson relation is at most the depth complexity of the associated function. So to prove this, what we're going to prove the equivalent statement. It says that equivalently given any circuit or formula, it doesn't matter because we are concerned with depth, but let me write just circuit. Computing f, we will design a protocol that computes KWFF. So what we are proving in so equivalently is that, so for every circuit that computes, okay, yeah, that computes KWFF, and the most important thing is that for every circuit, let me call this C, such that, okay, let me call this protocol pi, such that the depth complexity of C is 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 equal to the communication complexity of pi. So basically, from every circuit that computes F, we will get a protocol whose communication complexity is the depth of that circuit, and it correctly computes Kw of F. So if you remember, the communication complexity of Kw of F is defined to be the minimum over all possible pi that solve Kw of F and the communication complexity of that pi. So if you take any pi that correctly solves Kw of F, the communication complexity of that pi is going to be an upper bound for this value, right? Because this CC is a minimum, so any pi, this is going to be the, it's an upper bound for any pi that solves Kw of F. Okay, so, and what the equivalent theorem that we prove would establish that this communication complexity is exactly the depth complexity of C. Okay, now we need to, but if you remember, we wanted to connect it to depth complexity of F. So if you remember, the depth complexity of F is the depth complexity of the best C that computes F. So, and the equivalent theorem that we proved, that this depth of C is equal to communication complexity of pi, it's true for any circuit that computes F. So if you plug in C to be the optimal circuit that computes F, so just a side note here, if C is depth optimal circuit computing F, then we know that depth of that particular circuit is exactly equal to depth of F. So this fact, along with what we have derived, proves that the communication complexity of the Kashmir-Wigderson relation is upper bounded by the depth complexity of the corresponding function. So I think I went a bit fast on that. So there's some subtleties, right? I mean, we are not proving it directly, we are proving something equivalent, and there's this minimizations that happen, but they're like, if you think about it, they're very natural definitions. So are there any questions? Okay, if not, let me continue. So the main thing that I want you to remember is that, okay, so we're going to prove equivalently that from any circuit that computes F, we can get a protocol that computes the associated Kashmir-Wigderson relation, where the communication complexity is equal to the depth complexity of the circuit. So here is, so let me prove this by an example. So let's take the, so I want to take a concrete example. So let's consider the communication, the Kashmir-Wigderson relation of the parity function. So let's take the 2-bit parity function. So if you remember, 2-bit parity function is just this function which takes two inputs. So maybe not a good idea to call it x1, x2, because we're going to assume that x is the input to Alice and y is the input to Bob. So let's call it z1, z2 to represent all possible inputs. And the parity function is like 0, 0, it's 0, 0, 1, it's 1, 1, 0, it's 1, and 1, 1, it's 0. And if you remember from the very first lecture, here is a simple formula that computes the parity function, the 2-bit parity function. So okay, yeah, so I should have mentioned, so whenever I say circuit here, this are circuits, De Morgan circuits, which we saw that in the first lecture, are circuits whose internal gates are AND and OR. Internal gates are AND or sorry, so AND is like denoted by this, and OR, and they have fan in exactly 2. So you're not allowed to use any other complex gates, and this only holds over these kind of circuits. So this Kashmir-Wigderson connection from communication complexity to circuit complexity holds over this specific family of circuits where all the negations appear at the leaf, and all the internal gates are either AND or OR, and any internal gate can only look at two other inputs. So every, and yeah, so these are, so this is over, so the depth, yeah, so the depth is defined over such formulas or circuits. Okay, so here is a De Morgan formula computing parity function. So you want to take, so sorry, so an equivalent expression for KW of, like for the parity function, the it's x1 x2 bar plus x1 bar x2, right? So equivalently you can write this as a formula where you take the OR of AND of x1 and x2 bar. So I'm not going to explicitly write that negation gate from now on. I'll just put a bar if I want to negate it later. And x1 bar x2. So here's a circuit. So how is this circuit connected to solving the Kashmir-Wigderson relation? So if you remember, so what is the Kashmir-Wigderson relation? So again, I don't want to represent these bottom gates by x or y because they're going to have a specific meaning. So we'll represent it by z1 and z2. So this is z1 z2 bar and z1 bar z2. So what was the Kashmir-Wigderson relation? So here two players, Alice, who gets an input where parity is 1, So this 2-bit parity is 1, and Bob gets an input where this 2-bit parity is 0. So as we are considering an example, let's give some concrete inputs. Let's say Alice gets 0 1 and Bob gets 1 1. So you can clearly see that so in the first input it's the function evaluates to 1, and the second input the function evaluates to 0. So hence these inputs are different, and the goal of the Kashmir-Wigderson relation was to find an index I in n. So n was the number of inputs to the function f. So here in this example it's 2. So you have to find an index, either it's index 1 or index 2, such that xi is not equal to yi. And then this specific example, there is only one such index, right? So there's a unique answer for this input, and that answer is index 1. So on index 1, x1 is 0 and y1 is 1. Yeah. On index 2 they agree, x1, x2, x1 is 1. So what we want to prove, so like remember our intermediate goal and for this example is that we want to come up with a protocol design a protocol such that communication complexity of that protocol, so protocol pi, such that communication protocol complexity of this protocol is equal to the depth complexity of the circuit that we given. And if you remember the circuit that we are given, what's the depth complexity of this circuit? Depth complexity of the circuit, if you remember, is the longest path from root to the output to one of the leaves, one of the inputs. And for this circuit it's very balanced on every path, the length is exactly 2. So we want to sort of communicate 2 bits and then find an index where they differ. So here is an idea. So, and I'm going to write down this specific inputs. Alice and Bob are given. So Alice is given 0 1 and Bob is given 1 1. So they both know the circuit, right? I can assume that they both know the circuit because they both know the function. They can, in a protocol, you can come up with some kind of a priori agreement which does not depend on the specific inputs that you are given. So they can a priori like come together and discuss and say that okay, we are going to use this very specific circuit. So they both know the circuit that they're going to use, and the circuit is going to be the one I drew in this example. So if you remember, so I'm gonna not write z1 and z2, I'm gonna plug in the values of z1 and z2. So it was z1 z2 bar, so here z1 is 0 for Alice, it's 0, and z2 is 1, so the complement of 1 is 0, right? And there was an OR. So this and so what's the output of this AND gate? It's 0, right? So it's 0 and 0, and the other AND was on z1 bar, which was 0 bar, which is 1, and z2 is 1. So what's the output of this AND gate? This is 1. And what's the output of the entire circuit? It's 1. And this is what you would expect, right? This is a circuit that computes a function. So given an input, it should output the value of the function. So the Bob knows the circuit, but Bob doesn't know what Alice's evaluations are like. He knows the structure of the circuit, and similar with Alice. Alice knows the structure of the circuit. She knows her evaluations. She doesn't know what Bob's evaluations are. So what Bob knows is this. So again, this circuit, and I want to write down his particular view. So Bob gets the input 1 1. So z1 is 1, and z1 bar, z2 bar is 1 bar, which is 0, and z1 bar is 1 bar, which is 0, and z2 is 1. So what is the output of this AND gate? That is also 0, right? And this AND gate also is 0 because one of the inputs is 0. And what's the output of the gate OR gate? It's 0. So as expected, it computes parity on 1 1, which should be 0. And common knowledge, as I was telling you, is the structure of the circuit, but the evaluations are not like each player only know their evaluations. And remember, the goal is to find, so goal is to find I such that xi is not equal to yi. So how do we design a protocol using this circuit? So here is the idea. So both Alice and Bob know that their outputs differ, right? Alice knows that her output is 1 and Bob knows that his output is 0. And they know, like, they both know the circuit, so they know what kind of gate sits at the output. So what's the gate here? It's OR. So what's the property of the OR gate? If OR is 0, so if the OR gate is evaluates to 0, then both its inputs must be 0. So OR evaluates to 0, then it should see both 0 0. So by this I mean, like, okay, one of them, like both of them should be 0. But in case it evaluates to 1, at least one should be 1. At least one of the inputs should be 1. We don't know what that input is, but at least one of them should be 1. So Alice knows that Bob's evaluation is, like, Bob's evaluation on this OR gate is 0. So she knows, without knowing what Bob's inputs are, she knows that this OR gate sees a 0 on both of its input. And similarly, Bob knows that Alice's evaluation on this OR gate is 1, and by the property of this OR gate, he knows that Alice should be seeing a 1 on either the left child of the um, either the left child or the right child of this OR gate. The problem is that he doesn't know which one. Okay, so he knows either if you go left or if you go right, you would see a 1 because Alice's evaluation is 1. So our goal is, like, so remember, like, the amount of uh, like communication that we can spend to prove that the communication is exactly equal to depth complexity is 2, because the depth of the circuit is 2. So we want to, like, somehow use 1 bit of communication each time and then somehow reach an input. So we want to, like, simulate the players to go through this circuit depth layer by layer so that they will reach the input after, like, 2 bits of communication. So here is what they're going to do. So first, by this property of the top gate, the OR gate, Bob knows that one of Alice's inputs should be 1. So that's some useful information. But there's an asymmetry here, right? Alice doesn't need any information about Bob's evaluations. Since the output is 0, she knows that both of his inputs are going to be 0. There's no information that Alice needs to know about the inputs of this top gate, but there's some information that Bob needs to know about Alice's top gate. So what is Alice going to do? Alice is going to send left or right, which you can encode with 1 bit, right? So they can a priori agree that if Alice or Bob send 0, that means it's the left child that is 1, and if say they send 1, that's the right child that is 1. So left and right are there are, like, 2 options, and you can encode with 1 bit, 1 Boolean bit. So Alice sends but I'm not going to write that encoding, so I'm just going to say left or right. So Alice says, okay, so in this particular example, Alice knows that it's the right child, so this is right for me and this is left for me, so that's the convention that we'll stick to. So Alice knows that it's the right child where she has a 1. It could be that in some input, like maybe they both are 1, but in this circuit that will never happen. But she knows that at least one of these inputs should be 1, and she knows both of them. So she says, okay, Bob, go left. So I'm just writing this specific example. So sorry, again, confusion. So Alice says go right in this example. Sorry, I have this habit of confusing left with right. So if you find any mistakes, let me know. I might confuse. So Alice tells Bob, you go right. So then Bob knows that, okay, so he will interpret this message as if we can add different color, so they're going to, so Bob will ignore the, both Alice and Bob will ignore the rest of the circuit, and they will just focus on this left, sorry, the right part. So they're going to ignore this and they're going to ignore this. And so at the beginning, so we're going to use some kind of natural invariant which works every time we send a bit, or equivalently every time, every layer that we descend in the circuit. So in the beginning, Alice and Bob knew what the output of the sub circuit that they were focusing on. Initially, the circuit they were focusing on was the entire circuit, and the output of that circuit should be the evaluation of the function. And by the promise given in the problem, they know that Alice sees a 1 and Bob sees a 0. And now, even for this sub circuit, they know what the output of the root is, because, okay, so from Bob's perspective, since Alice said go right, he knows that Alice sees a 1 here. Okay, so Alice is going to describe to a Bob a direction where she sees a 1. So because that's the pre-agreement, he knows that Alice's output is 1 on that gate. And Bob, so from the perspective of Alice, because she knew that Bob's output here was 0, no matter where she goes to, Bob will see a 0. This is important. So Alice, without communication, knows what Bob's output is going to be here, and that's going to be 0. And if you see, it's again a 1-0 separation, right? So Alice on this sub circuit, so they've discarded a large portion of the circuit, and in the sub circuits that they both are focusing on, they both know what they're focusing on. Alice sees a 1 and Bob sees a 0. So this is a kind of a recursive regime, right? Because we have maintained this invariant that every step they know a sub-circuit where Alice, on the output, Alice sees a 1 and Bob sees a 0. But there's some subtlety here. So who speaks first depends on the kind of gate that they are looking at the output. So because this was an OR gate at the root of the circuit, Alice knew it was her turn to speak, so Bob would keep mum about it, and then he will wait for Alice to send a bit. So this is going to be, this is a subtle thing, and it's going to be important later on for when you consider some kind of generalization called multiplexer relation, etc. But for now, uh, understand the point that by looking at the circuit, like Alice and Bob know which one of them is supposed to speak in a round, and that's completely determined by the circuit. So you don't need communication to do that. So now we are at this interesting sub-circuit. So let me just erase the rest of the circuit. Maybe I'll just keep it like, yeah, doesn't matter. So now what is the gate here? So this is an AND gate. So similar to the observation that I had written here, I want to write as observation for AND gate. So again, there's an information asymmetry. So if you have an AND gate that evaluates to 1, so what do you know about the inputs of this AND gate? Both the inputs should be 1, right? That's the only time an AND is a 1. And if the AND evaluates to a 0, then we know that one of them should be a 0. So like in the case of OR, in one of the inputs, we know what the, so for one of the outputs, we know what exactly the inputs are. And for the other, the complementary output, we know that at least one of them should be a constant. And in this case, we know that at least one of them should be a 0. So who do you think should speak in this round? Any guesses? So in the last round, it was an OR gate, and the asymmetry favored Alice. So here, who does it favor? Any guesses? Yeah, it is Bob. It's, yeah. So because Alice has no useful information, she knows that she sees a 1 on both her children, and Bob, thanks for the answer. Bob knows that, yeah, Bob has useful information. So he might not see, like he has to see a 0, but he might be see both 2 zeros or 1 0, but he has to see at least once, like at least one. And so this round, what Bob is going to do is Bob is going to say in this specific example, so where should Bob go? So on the left of Bob, it's a 1. That's not useful information for Alice. So on the left of, sorry, again, I made this confusion. Sorry about that. So on the right of Bob, it's a 1. So that's not a subcircuit where Alice and Bob are differing. They both see a 1. So that's the boring part. So the interesting part is the left child of Bob. So Bob says, go left. Okay. So now I claim that we are sort of done. At least one of the players know the answer now. Why is that? So what is happening here? So where did we? So they both know the circuit. So they know that after this round, what are they going to do? They're going to discard again another sub-circuit. So that sub-circuit that they're going to discard based on Bob's input is this. So they're just looking at a very simple circuit. And what is that circuit? It's just a literal. It's either a variable or its complement. And what is the sub-circuit they're looking at? If you remember from the diagram that we drew, that is this input Z1 bar, right? Yeah. So they know that they're at an input, and they know what the input is labeled by. They know it's in this example, they know it's Z1 bar. But the sort of invariant that they maintained said that on this input, Alice would see a evaluation that is different from an evaluation that is Bob's, right? So in fact, like we maintained a very strict invariant. It said that Bob's subcircuit always outputs 0 and Alice's subcircuit always output 1. So we maintained it for all the 3 subcircuits that we considered. So in the beginning we considered the entire circuit, then we considered this thing that marked in blue plus the left child. That again, for that circuit, the output of Alice was 1 and the output of Bob was 0, and we maintain this invariant while going into an input. So we know that output of Alice is 1 and output of Bob is 0. So then we know that, so this was Z1 bar. So they also knew that what is this literal, so C1 bar. So what's Alice's evaluation of C1 bar? That is just X1 bar. So X1 bar is 1. So at the end of this, Alice and Bob know this. Oh, sorry, in the end of this, Alice knows, maybe Bob doesn't know. Okay, actually Bob also knows. Alice knows that X1 bar is 1 and because Bob would be seeing Y1 bar, she also knows that Y1 bar is 0. So then she knows that index 1 is a place where they differ, right? So if X1 bar is 1 and Y1 bar is 0, then X1 should be different from Y1. If X1 bar is different from Y1 bar, trivially X1 should be different from Y1. So she knows that at index 1, their inputs differ, but Bob also knew where they went, and see, he also knows this information, so he also knows this, knows that at input 1 they differ. So for this concrete example, what was the communication complexity? It just took 2 messages, and each of these messages could be encoded in a bit. So the complexity of this protocol was 2 bits. Okay, but this is an example, but what we wanted was this very general proof that given any circuit, we can design a protocol where the communication protocol complexity of this protocol is exactly equal to the depth complexity of the circuit given. So I hope you understand this example well enough, and then you can prove this inductively for any general circuit. So what would be the inductive kind of argument? We'd say that, so at any point at round I, they look at so I'll think of dividing the circuit into like layers. Sorry, that's not the color I wanted to use. So we'll divide the circuit into like layers. So we know that the depth of the circuit is d, so this is going to be layer 1. So like in circuit complexity, I guess they sometimes people refer it, like mostly people refer it as layer d, but for the purpose of this proof, let's call this layer 1 and this is layer d. So because of the depth of the circuit is d, so we will have exactly like d layers. So what are we going to do at round I? We are going to be at round I, we are going to be at layer I, and we are going to look at one particular sub-circuit at layer I, right? So let's call this Ci, and we have this invariant that we maintain. Okay, so one of the invariant that we maintain is that the round I will be at layer I. We would have made I steps of progress. So the invariant that we're going to maintain is that for Alice's input Ci, so Alice's input x, Ci of x would be 1, and Bob's input y, Ci of y should be 0. And based on whether it's an AND gate or an OR gate, so this is where I was telling you that it's very important for this connection to work. It's very important that internal gates are either AND gate or an OR gate, because this we exploited this information asymmetry uh, to make sure that only either Alice or Bob needs to talk. So based on whether it's AND or OR, if it's AND, Bob will speak, and if it's OR, Alice will speak, and they will send a message which either says go left or right. So in general, if you zoom into this picture, it's going to look at so there's going to be some circuit, and it will have two circuits at layer I plus 1. One is the left child and another is right child. This is layer I plus 1, and based on the message in that round, they're going to go to either the left child or the right child while maintaining this invariant. And the cost of a round is exactly 1 bit, right? Because they're sending either left or right. And you need to prove that after d rounds, you would have reached an input literal. So they would have reached an input at round d or d plus 1. I don't know. I guess it's round d. Doesn't matter too much. They would know that the sub circuit they're looking at is just one literal. So the sum I in n, so the sub circuit CD is just either Zi or Zi bar. So what does this imply? That this implies that so CD is either Zi or Zi bar, and invariant tells you that Zi, so for example, CD of x so is 1 and CD of y is 0. But actually you can notice at this point that this circuit doesn't even look at the entire set of inputs, right? It just looks at one bit. So this is saying that, so let's take this to be the case without loss of generality. The argument is similar to the case. So in this case, we know that CD of x is equal to xi, and CD of y is equal to yi. So this guarantee, the invariant that we maintained, implies that xi is 1 and yi is 0. So hence I is a valid answer for the KW relation of f. So remember, the goal in the Kashmir-Wigderson relation was to find an index where the positive input differs from the negative input. So so, and the cost of this protocol is exactly d. So this is one direction. The other direction is it's exactly similar to the proof here, but what we do, what we want to say is that given a protocol that's, so let me tell you what you want to solve in the other direction. Sorry, not the other direction, the second, yeah, the second part. So second part was to say that communication complexity of, so the depth complexity of a function is upper bounded by communication complexity of the Kashmir-Wigderson protocol associated with f. So like in the case of circuits, what we are going to show is that equivalently we want to show that given a protocol, again whenever I say protocol in today's lecture, it means deterministic for those who know what this means. Okay, I've ran out of space here. Deterministic. By solving kw of f, we can construct a De Morgan, in fact, formula f computing the given function f such that the depth complexity of this specific formula is upper bounded by the communication complexity of the protocol that we started with. Sorry, actually equal to, like in the case. So even proving that it's upper bounded by that would do. And because depth complexity of f is minimum over all possible f that compute f, so you can take the, so if you take a specific formula that computes f, that's an upper bound on the depth complexity of f. Depth complexity of that formula is an upper bound on depth complexity of f. So it's as earlier as in the earlier case, you can see that depth of f is at most depth of f because f computes f for a trivial reason. F is one such formula that computes f, and depth of f is taken to be the minimum over all possible things. So depth complexity of f is upper bounded by the communication complexity of any protocol pi that solves the Kashmir-Wigderson relation. So by plugging in the best protocol that solves Kashmir-Wigderson relation, we'll get that this CC of pi for that specific, for pi, so the optimal protocol that solves the Kashmir-Wigderson relation of f, these two things are, this is going to be equal to the Kashmir-Wigderson, the communication complexity of the Kashmir-Wigderson relation. So we get that the depth complexity of f is upper bounded by the communication complexity of the Kashmir-Wigderson relation. So if you have not seen this before, it would be a good idea to just like sort of work this out for yourself. It's not too hard. Once you've seen this idea, it's not too hard. Both directions are not hard. So in this direction, we need to like the difference is that we need to take a protocol and convert it into a formula. So in the case of converting a circuit into a, we need to convert a protocol into a circuit or a formula, and in the case where we converted a circuit into a protocol, so whenever there was an AND gate, it was Bob's turn to speak, and whenever it was an OR gate, it was Alice's turn to speak. So what you do is that you take this protocol, and whenever Alice speaks, replace it with an OR gate, and whenever Bob speaks, replace it with an AND gate, and you can inductively prove that things magically work out. Okay, so it's a good idea to do this as an exercise, and for people who are crediting this course, I'm definitely thinking of including this as an exercise. But even if you're interested in this research direction, it's a fun thing to work it out. I'm pretty sure by now all of you know how to do this. Please let me know if you have any questions before we move on to the other part. Yeah. Okay. Yeah. Uh-huh. Uh, it's not necessarily the optimal protocol, but if you start with a circuit that is optimal for computing f, yes, it is indeed going to be optimal, but for a specific input, maybe not. But in the worst case, it's going to be optimal. So maybe for a specific input, like there are like crazier things that you can do, like yeah. But in the worst case, you're not going to be able to do better than that. So at the end of the day, what we proved is that, like, if you, okay, not proved, kind of intuitively saw, is that the communication complexity of the Kashmir distance relation of f is equal to depth complexity of f. So if you start with the formula that is optimal for depth of f, then you would get an optimal protocol for kW of f. But that is so optimality of a deterministic protocol is defined in terms of the worst case input. So yeah, so you're not going to be able to beat this on every input, but on some other inputs, like maybe some specific examples, you can do better than like doing this naive thing from tracing a path from the root to the left. Thanks. Interesting question. Yeah, yeah. Uh, so just to summarize, what we have proved is that, okay, if you understand the depth complex, if you want to understand the depth complexity of a function, just figure out what's the communication complexity of this associated relation. So now you can state the Krw conjecture in terms of communication complexity. So just to recall, I'm not going to write the conjecture in its entirety. Krw conjecture, if you remember, said that depth complexity of f composed G is approximately equal to depth of f plus depth of G, and Kashmir-Wigderson's result said that depth of f is equal to communication complexity of the associated Kashmir-Wigderson relation, and depth of G is the communication complexity Kashmir-Wigderson relation of G. And what's going to be depth of f composed G? No brownie points for guessing. It's Kashmir-Wigderson relation associated with this new Boolean function, which is f composed G. Yeah. So Krw conjecture restated in terms of communication would be the following: the communication complexity of the Kashmir-Wigderson relation associated with this new Boolean function that we get out of f and g should be approximately equal to the communication complexity of Kw of f plus communication complexity of Kw of g. So nothing magical here. We just used this very strong bridge that said that these two things are equal, and then just rewritten d of g as communication complexity of g, Kw of g. Yep. So I promise that, okay, at the end of the lecture we'll also, like, if you are a skeptic and you don't believe in the conjecture, we'll see a gap example. I don't know if I'll have time for that, but I just wanted to tell you, I want to describe what is a Kashmir-Wigderson relation associated with the block composition of f and g. So it's going to be an interesting object, and we're going to use that in the upcoming lectures. So yeah. Okay, so what is the Kashmir-Wigderson relation? Sorry. Um, so what is the Kashmir-Wigderson relation associated with f composed with g? So by definition, Alice should get an input. So let me call it capital X. It's, so if you remember, we always think of the input to f composed g as a matrix, and in general, I'd use capital inputs to denote matrices, and small like the small letters to denote usual binary strings. So Alice gets an X, which is a one input of f composed G. So she gets it from f composed G inverse 1, and Bob gets an input Y such that f composed G evaluated on Y should be 0. Oops, 0. Yeah. But let's try to understand what does it mean. So, so I was telling you, we're always going to think of x and y as matrices. So if f is an m-bit function and g is an n-bit function, so f compose g was mn bits, right? Oops. Mn bits. So x is m by n matrix. So they're going to be like rows 1 to m, columns are going to be 1 to n, and similarly, okay, I understand that, okay, I should be drawing two equal size matrices. I can copy this one over maybe. No, I'm not gonna. So for some reason it gives me zoom. So this diagram has not two proportions. So Bob gets again an m by n matrix. I'm not gonna write m by n, but again it has like, yeah, this is m1 to m. It has columns 1 to n. So what does it mean to say that x evaluates to 1 and y evaluates to 0? So if you remember, the way we defined this block composition was, so let me make this matrices smaller so I have some room to, okay. Okay, so the way we defined f compose g was first apply g on individual rows of an input, right? So the rows are, let's say, x1 to xm. So we apply g on x1, g on xm, blah blah blah, and then we get a vector. Let me denote that by a. So we get a vector, and that vector is another Boolean bit string based on the evaluations of g. So we are not guaranteed anything about a other than the fact that if you evaluate f on a, what should be the answer? F of a should be 1, right? Because f compose g on x by definition of this block composition is f of a, right? Because ai is equal to g of xi. Okay, so given an input x, Alice can actually without communication compute this extra input, which is a vector, and let's call that a, and that, so we are guaranteed that this vector a, when given as an input to f, should evaluate to 1. So this is what it means to say that f compose g on x is 1. Okay, so similarly Bob can do the same trick, and he will get a vector with, let's call it b. Again, it's going to be a 0 1 vector with m entries. So when f is applied on b, what should be the answer? It should be 0, because f compose g on y is, so this was 1 and this is 0. This is equal to f of b, where because for all I, bi is g of yi. And what is the goal here? So the goal of the Kashmir weak decision relation is to find an index where the players differ. So goal is find, so again, from now on we're going to think of these inputs as matrices, right? So I want to index them as matrices, so I want to find an index I comma j such that xij is not equal to yij. So as matrices, so this, since they are matrices, I want to index them as matrices. So I want to find a row I. So I want to find some row I. Let's say this is row I. And then inside that row, we want to find a column. Let's say it's the first column where the inputs differ. So this is 0 and this should be 1. So if you think in terms of the matrix, the goal of the Kashmir-Wilderson relation is for the players to find a row and a column so that the corresponding entry is different for Alice and Bob. And such a thing should always exist because the inputs x and y as matrices should be different, because f compose g of x is 1 and f compose g of y is 0. As we have argued earlier, x and y cannot be the same thing. So why did we introduce this auxiliary inputs? So if you remember, one direction of the conjecture, the only direction that we can prove, said that so the EC direction. So I see that I'm like almost out of time, so I'll wrap it up in like 5 more minutes. So if anyone has to leave, you may. I am of course going to upload this to YouTube within a day or two. So here is like the thing. So the EC direction of the Krw conjecture said that depth of f compose G is at most depth of f plus depth of G. So this was done by this specific circuit that computed f compose G. So what did we do? We took the best circuit that computes CF and best circuit that computes CG, and in this parlance, G is applied on x1 to xm, right? So x1 xi's denote Alice's input and yi's denote Bob's input, and if I don't want to discriminate it whose input it is, so I'll just denote it by zi. So it's the ith row of the input matrix. So the circuit computes G on C1, Z2 up to Zm, right? And then it gets these values, so and then feeds it into f, and that computes f compose G. So the depth of so this is a circuit that computes f compose G, and its depth is the depth of f plus depth of G. So equivalently, in the communication analog, so what should be the thing that we want to prove? That the communication complexity of Kw of f compose G is at most the communication complexity of Kw of f plus communication complexity of Kw of G, right? So how do we prove this? So in the circuit upper bound, we use this the best circuit for C of f, and the best circuit, so best circuit C of f, and the best circuit C of G in terms of depth. So we're going to use similarly the best protocol that solves the Kashmir-Wilderson relation, and we're going to have this view of the inputs. So remember, okay, so what is this? So what is the setting? So the communication, so the Kashmir-Wilderson relation associated with f of compose G. So Alice gets an input x, which is a matrix, and if she applies G on individual rows, by applying G, she gets an auxiliary input A such that f of A is 1, and Bob gets a matrix Y, where if he applies G, he gets an auxiliary input B. Note that to compute this like the auxiliary inputs, there's no communication needed. They can do it individually. Again, Alice won't know what B is and Bob won't know what is, but that's a setup anyway in communication complexity. And you're guaranteed that f of B is 0. This is just by definition of block composition. So I want to prove that the communication complexity of Kw of f compose G, so to do is at most communication complexity of Kw of f plus communication complexity of Kw of G. And the goal here was to find an entry which was the same entry in this two matrices where their inputs differ, right? So what I'm going to do is like I'm going to use the best protocol for this one. So let me call it pi f, and the best protocol for this one, let's call it pi g. and get a protocol, let's call it pi f compose g, that solves this problem. And the communication complexity of pi f compose g would be communication complexity of pi f plus communication complexity of pi g. So what are we going to do? So remember, in the Kashmir-Wigderson relation of f, what was the setup? Alice gets an input A, so I'm going to deliberately write A, which was from f inverse of 1, and Bob got a B, which was f inverse of 0, and the pi f is supposed to, pi f when on inputs A and B is supposed to output an index such that AI is not equal to BI, right? So what Alice and Bob are going to do, so they compute A and B without any communication. They run pi f on the input instances A and B. So then they will get an index I such that, so let's assume that that index was the last index. So they get that after running this protocol, they get that AN is not equal to PN, right? So they know, and let's say they also know the value of AN and PN at this point. So they figure out this is 0 and this is 1. So after running the protocol PyF, they know an index where AI is different from BI, and let's say it's AI equal to 0 and BI equal to 1. But the goal of the Kashmir-Wigderson relation associated with F compose G is not to find a difference in these vectors, but to find a difference in the actual matrices, right? So these auxiliary inputs are not even part of the definition of KW of F compose G. So what do we do at this point? So what have we used? We have used pi f, and what do we have in hand? We have pi g. So what was the setup for KW of G? So it was just, again, replace everything f with g. So you're given some, so let me just, so are there any questions at this point? So this was this, so the protocol pi f compose G runs in 2 stages, and this was the first stage. So if there are no questions about the first stage, the second, to describe the second stage, let me remind you what is KW of G, but I'm going to denote the input so it's specific. Sorry. KW of G, whereas Alice gets an input. So deliberately I'm going to write xi such that G of xi is 1 and yi such that G of yi is 0. So now if you think about it, we know that if G is applied on, so in this specific example, if G is applied on xn, that is AI, and G is applied on yn, that is bi. So we know that on the nth row, the evaluations of G differ. So it is actually an instance of KW of f of G. So I say that, okay, so forget the matrix, and you look at only the row that you found where AI and BI are different. If you look at that specific row, in this example I've written xn and yn, that is an instance of KW of G. So KW of G, xn and yn are valid inputs. But in the definition, we always assume that Alice would see an evaluation which is 1 and Bob would see an evaluation which is 0. But in this case, for example, in this case, we got not so lucky. Alice gets G of xn to be 0 and Bob gets G of yn to be 1. But the protocol pi g, which solves KWG, assumes that Alice has a 1 input and Bob has a 0 input. So what do? They just run this protocol with the roles of Alice and Bob switched. So that's a subtle point, but if you think about it, you can convince yourself that's not a problem. So they can internally, so they at the end of first stage where they solved the protocol pi f and got an index where AI is equal to not equal to bi, and in that index they assume that they know the value of AI and bi. So based on the value, if Alice holds AI which is 0, so then she'll run pi g thinking that she's Bob, and Bob will run pi g thinking that he's Alice. But if Alice indeed got a row xi where G of xi was 1 and Bob got a row where G of is ought to be 0, then they will run pi g thinking that Alice is Alice and Bob is Bob. So at the end of the first round, they have an instance, which is an instance of kw of g. So they run the protocol pi g on xn and yn. So what would that give? So pi g on xi and yi would give so xi and yi are rows, so they are indexed from 1 to n with j. So they will find it will find a j such that xij is different from yij. And remember, this is the final output that we are supposed to produce in kwff compose g. So this shows that the communication complexity of pi of f compose g is exactly equal to communication complexity of pi of f plus communication complexity of pi of g. Yeah. So this is just the same proof. This nice circuit upper bound translated as a communication upper bound. Okay. So I don't think I have time to go into the example, the gap example. So or the description of the universal relation. So we'll stop here for now, and we'll meet next week. And there's office hours coming up, and so far I've decided on Friday 11 to 1. It's on the website, so maybe see some of you there. And thank you very much. And if there are any questions, I'm gonna hang around and we can discuss.